Good evening, everybody.
Good evening.
Yes, this is the first of two shortish talks, and the first one, as you can see, is keeping an eye on the universe. It's looking generally at what telescopes can tell us about how the universe works. So we know that telescopes have been around for a long time, of course. For the last 400 or so years, Galileo was one of the first to take a telescope and point it at the sky. He wasn't necessarily the first to use a telescope, but he was one of the first to point it at the sky and document and record what it was he saw. Since then, since the early days of telescopes that have used lenses to focus the light, most telescopes have used mirrors. This one with a small mirror in the back end of the telescope. And of course, more recently, telescopes have got larger and larger for two reasons. A, we want to collect more light to see fainter and fainter objects. And secondly, because the larger the mirror, the more detail we can see in the objects we're looking at. And so telescopes over the centuries since Galileo have got larger and larger and larger. So of order 100 years or so ago, the Hooker telescope was the largest in the world, 100 inches or 2.5 meters in diameter. That was then superseded by the 5 meter or the 200-inch Hale telescope, also in California. And now, of course, we're used to the idea of telescopes not just being in major observatories in the world, but also being plonked up in space, get above the Earth's atmosphere, get above the blurring effect of the Earth's atmosphere. You can see more detail for a given size of mirror. Hence, we've had the Hubble Space Telescope in Earth orbit for more than 30 years now, and more recently, a couple of years ago, the launch of the James Webb, not in Earth orbit, but placed in a particular location out in space 1 million miles away. Even though we do now have a number of different space telescopes that are up there, the quest for ever larger telescopes goes on. So there are still big telescopes being built on Earth, some very big telescopes. For instance, the rather ridiculously named Extremely Large Telescope is being built with a mirror diameter of some 40 meters or so. And in terms of, we're not going to cover the entire history of how the telescopes have got to the point where they are now, but I think it's quite instructive to look at just some of the more recent telescopes in terms of relative sizes. So if we have a look at this diagram, this is a scale diagram of the sizes of various telescope mirrors to give us an idea of just how big these telescopes are getting. And if scale is defeating you, there is actually a scale human here, if you can just about make them out. Or if you prefer, in the bottom left, there's part of a tennis court, and in the bottom right, there's part of a basketball court. So that gives you an idea of scale. In the very top left, unfortunately laser pointers don't work on TVs, in the very top left is the largest lens that was made for a telescope, a 40-inch or approximately 1 meter diameter lens for the Yerkes telescope in America. And that's the smallest dot, effectively, that you can see in this image. So all of these telescope mirrors are substantially larger than the largest lens that's ever been used in a telescope. Again, in the top left, just a little bit down from the extreme top, is the 100-inch Hooker and the 200-inch mirror in the top there, which were the largest telescopes in the world about 100 years ago and about 50 years ago. But you can see there are a number of telescopes that are getting larger and larger in terms of the size or the area of the mirror. The largest at the moment, the largest telescope that's in use at the moment, is the Gran Telescopio Canarias, which is, as you can see, a hexagonal segmented mirror. It's not one solid piece of glass, so it's not circular. It's actually a lot of hexagonal components put together, and that gives us a mirror approximately 10 meters or so in diameter, and that's currently the largest in the world. By comparison, space telescopes don't have particularly large mirrors. Space telescopes are actually in the bottom left of this diagram. There's 4 of them: the Hubble, Kepler, Gaia, and the James Webb. The James Webb is probably quite recognizable, A, because it's the largest, and B, because, again, it's a hexagonal segmented mirror, rather larger than the others. But you can see even the Webb is quite small compared to all of the sizes of the telescopes on ground-based observatories. And that's simply because it's very difficult to get large telescopes up into space. It's difficult enough to make large telescopes in an observatory when you've got them bolted onto the top of a mountain, but if you have to put them on the top of a rocket and send them into space, then you have to worry about the size of the mirror and the size of the telescope. So the Hubble Space Telescope was determined by it had to fit into the cargo bay of the shuttle, and with the Webb they had to fold it up in order to get it out into space. But you can see that there are much larger telescopes coming online. If the yellow at the very top is the largest we have at the moment, you can see on the extreme right there two very large telescopes, a 30-meter and a 40-meter diameter mirror telescopes are on the way. They're a little bit behind schedule, mainly because of COVID and a few other factors. It would have been nice to say that they would have been ready for the early 2020s. It looks like it's possibly going to be the late 2020s by the time these telescopes actually come online. And of course, the Hubble itself is absolutely iconic. It's not only astronomers who recognize this. I would argue that you could show this image to virtually anybody, even the man in the street who doesn't necessarily have any interest in astronomy. They would still recognize this as the Hubble Space Telescope, because over the 30 or so years it's been operating, it's produced some wonderful images. So let's have a look at a few of them. The Hubble Deep Field, when the Hubble was first put into service, various objects were identified as worth looking at with the Hubble Space Telescope, but also it was decided, let's have a look at a patch of sky where we think there's nothing and see what's out there. In other words, find a patch of sky where we don't think there's actually anything there and take a very long exposure and see what's out there. And then you find that there are thousands of galaxies in a very small patch of sky, and that tells us, roughly speaking, how many galaxies there might be in the observable universe. So that was an absolutely crucial image because it basically tells us how big the observable universe is. If we see thousands of galaxies in a small patch of sky, we simply scale that up for the whole sky and say there must be something like 1 trillion galaxies or so out there to be seen. And just to show you what a small patch of sky the Hubble was actually looking at, if we think of a patch of sky and we've got the moon there to scale, just to give us an idea of how big this is, remember that the moon can be covered with the little fingernail of your hand, of an outstretched arm. So the moon is only half a degree or so in the sky, and the size of the Hubble Space Telescope field of view is that small rectangle there, a tiny fraction of the area of the full moon as seen from Earth. So you can appreciate that if you wanted the Hubble Space Telescope to look at the entire sky and take an image of everything that's out there, given it has such a small field of view, it would take 100 years or more for the Hubble to actually map out everything. So the Hubble has to be told, there's an object of interest, go look at it. There's another object of interest, go look at it. The Hubble is not scanning the sky looking for interesting things, it's told what to look at. And just to prove that that little patch of sky that it looked at that contains thousands of galaxies, just to prove it wasn't a fluke, it looked in the opposite part of the sky, in other words, in a different direction, took another deep field, and again, it's not, of course, the same galaxies, because we're looking in a different direction, but it's a similar distribution and a similar number of galaxies looking in a completely different direction. And that convinces us that that's what we would see if we looked essentially in any direction from where we are at the moment, and that allows us to estimate the total number of galaxies in the observable universe as many hundreds of billions, perhaps 1 trillion or so. But of course, if we look at closer objects, in the Hubble Deep Field, we're looking at galaxies that are very large distance away. If we look at closer galaxies, we see them in incredible detail, either with large telescopes on the ground or with the smaller mirror, but the Hubble Space Telescope has the advantage of being above the Earth's atmosphere. So for galaxies that are relatively close to us, we can get amazing detail. And of course, pictures like this, images like this, help us understand how galaxies evolve, because we can take images of hundreds or perhaps thousands of galaxies, which are all not too far away, so we can see them in amazing detail. We can get a good idea of how the stars are being born within those galaxies, why they form spiral arms, how they evolve, and we can also see not only individual galaxies, but we can see galaxies that are in the process of interacting with other galaxies. Unlike stars, which tend to be a very large distance apart compared to their sizes, galaxies are often not separated by huge distances compared to their size. In other words, if you think of the size of the Milky Way and how far it is to the Andromeda galaxy, Andromeda isn't many times further away than the physical size of the Milky Way or the size of Andromeda, whereas the nearest star is a lot further away than a few diameters of the Sun. So it is not that unusual to find galaxies interacting with each other, because relatively speaking, they are quite close to each other. And so once we started to get telescopes that had enough resolution, enough detail to show us what these galaxies look like, we found more and more examples of galaxies interacting with each other. Even though we might have assumed that every galaxy is completely isolated from all the others, in fact, it is very common to find them interacting. In this particular case, it looks like a spiral galaxy at the top has been somewhat disrupted by this galaxy at the bottom, and perhaps vice versa as well. So perhaps these were galaxies that started off looking like spiral galaxies similar to our own or similar to the Andromeda galaxy, but because they got a little close to each other, the gravity from one is affecting the other and disrupting the nice spiral pattern. In some cases, we see galaxies in collision. So this is two galaxies that have actually effectively smashed into each other in the process of merging, which is not as cataclysmic as it sounds, because these, I'm doing it again, pointing at the screen where you can't see the laser, the pink areas in this sort of image are telling us that although the individual stars of galaxies are not likely to collide with each other, all of the gas and all of the dust of the two galaxies does collide, and it tends to trigger new star formation. So everything you can see here in pink is probably new star formation. So far from galaxy collisions being cataclysmic end-of-life scenarios, they're actually a new beginning. In many cases, the new stars being born rejuvenate galaxies because they collide and merge with other galaxies. And this is a lot more common than we first appreciated, and now we've got a much better idea of how galaxies evolve, because we can look at this happening. We can't watch it happening in real time, but we can look at lots of pairs of galaxies or collections of galaxies that are colliding, and from that we get the story of how galaxies are likely to have evolved since the early universe. If we look within our own galaxy, of course, we get a much better idea of how stars behave by looking in detail at particular star systems. For instance, this is the Helix Nebula. This is visible in amateur telescopes low down in the south during the summer in the constellation of Aquarius. And this is a star that's come to the end of its life. The star itself is the tiny white dot now in the middle, but the outer part of the star has been blown away to produce this so-called planetary nebula. In other words, a lot of hydrogen and helium has been lost from the outer part of the star. That produces the planetary nebula, so called simply because in very early telescopes it looked like a disk, it looked a little bit like a planet, and they weren't sure what they were. But now we know that these are large clouds of hydrogen and helium that have been blown off from the star. They're probably light years or so in diameter, and the small white dot in the middle is what's left once that star has lost its outer atmosphere. It's a white dwarf. And we think this is what's going to happen to the Sun. When the Sun runs out of its nuclear fuel in many billions of years' time, this is what's going to happen. The outer part of the Sun will swell up and be lost into space, and the core of the Sun will end up as a white dwarf. So if you could observe this from far enough away, this could be what the Sun is going to look like in a few billion years' time. Some stars are massive enough that when they come to the end of their lives, they don't die gracefully by just making a planetary nebula and then forming a white dwarf. If the mass of the star is high enough, then when the fuel eventually runs out, gravity takes over and the entire star collapses and there's an enormous rebound effect which blows the star to pieces, and effectively there's either very little left or almost nothing left. It might be that what you're left with is a neutron star or a black hole, but most of the material of the star gets blown away into the interstellar medium. And this is the familiar Crab Nebula, Messier 1 or M1. This is first observed by the Chinese in 1054, so this, the actual supernova was something like 1,000 years ago as seen from Earth, and it's been expanding ever since. Perhaps even more spectacular is another supernova remnant. The previous image, the Hubble managed to image essentially all of the supernova remnant, but there's another remnant of a supernova in the northern hemisphere called the Veil Nebula, which is so large the Hubble can't possibly capture everything in its relatively small field of view. So the top inset in the top left is an amateur picture that shows us the whole of the Veil Nebula. This particular star must have exploded probably tens of thousands of years ago, and hence the supernova remnant isn't a relatively small object like the Crab. It has been expanding for many, many thousands of years and has produced this sort of bubble, if you like, that you can see in the top left. It's much larger in apparent size as viewed from Earth than the full moon. It's something like 3 degrees or so in diameter. And so the Hubble would spend the next few years trying to image the whole thing by trying to make a mosaic. So they've restricted themselves to simply looking at part of the Veil Nebula, indicated by the red rectangle there. And so this image we're looking at, the main image, is just the tiny part shown by the red rectangle. And the colors are not arbitrary. The colors have been assigned by taking an image with particular filters that show us the light from hydrogen, the light from sulfur, and the light from oxygen atoms, and then they've been colored red and green and blue respectively. So not only can we see its beautiful image of the shock wave of this supernova expanding out into interstellar space, an astrophysicist could look at that and say, well, the colors tell me what the hydrogen is doing, or what the sulfur is doing, or what the oxygen is doing, and hence get a better idea of how this supernova went off and what this shock wave is now doing as it travels through the interstellar medium. It effectively gives us some information about the supernova itself, and it gives us information about the medium through which this shock wave is traveling. So it gives us information about what is sitting in between the stars. So images such as this, with all of the amazing detail that we get, this would probably keep a PhD student busy for years analyzing this one image to try and understand exactly what is going on in terms of how the shock wave is propagating. There's plenty of phenomena that occur on much larger scales, not just scales within our galaxy, not even scales between galaxies, but on cosmological scales across the entire observable universe. It is possible to do these experiments with ground-based telescopes, but the Hubble has made it easier in the sense that without the blurring effect of the Earth's atmosphere, it's been able to see some of these rather subtle effects, including this one that was seen quite a few years ago. It's called gravitational lensing, whereby if you look at what Einstein says about how matter makes the universe behave, it tends to distort space in such a way that light, instead of traveling in straight lines, will travel in a curve, as if there was a large lens where there's a large mass sitting in the universe. So here there's a large galaxy cluster, these slightly orangey blobs in the foreground. And this is acting like a lens so that light from more distant objects gets focused by this lens and makes these more distant objects brighter and easier to see. Not only that, because the lens is imperfect, a distant object might get imaged more than once because it's not a perfect lens that takes light from a distant object and produce a single image which we can then see on Earth. So that galaxy that's shown in the little white box there is actually imaged more than once. I can't easily point to the other examples, but that same galaxy is also imaged in the top left of this particular crop that I've taken of the original image. The same galaxy is imaged more than once. Not only that, but if we blow up the image, as shown by this inset, notice that it seems to have 4 bright points of light in it. It's as if 4 supernovae have gone off at the same time. That is extremely unlikely in any given galaxy. You wouldn't expect a supernova more often than about once per century or so. So the chances of 4 going off at the same time are very remote. So it's been concluded that actually what we're looking at there is the same supernova imaged 4 times because of the way light has been distorted or bent or curved as it passes through this galaxy cluster. And it's lots of images like this taken with the Hubble and taken with ground-based telescopes that have allowed us to work out how much matter must there be in order to produce these sorts of effects that were predicted by Einstein 100 years ago. And when you calculate how much mass you need to produce these effects, it turns out there's far more than you can account for simply by looking at how many stars appear to be there, judging by how bright these galaxies are. So that tells us there's more in the universe than simply the matter we can see. It tells us there's something out there which we're now calling dark matter, but we still don't actually know what it is. Lots of nebula, lots of star-forming regions within our own galaxy have been imaged and produced beautiful images such as Mystic Mountain in the southern hemisphere and the famous Pillars of Creation visible from the northern hemisphere in the Eagle Nebula. And again, this is promoted and developed our understanding of star formation and star birth in nebulae such as these, nurseries such as this. Now, of course, I've been talking a little bit about the Hubble Space Telescope. We know that that has now been joined by the James Webb. It's not been replaced by the James Webb. This is now an infrared telescope, which is complementary to what the Hubble has been doing. But as I'm going to be talking about the James Webb and what the James Webb has been doing in the next short talk, I'm going to skip over that and think about another telescope which will be coming online before too long. It's got the rather awkward name of the Large Synoptic Survey Telescope. It's actually been renamed because of a donor with some cash. It's been renamed the Simonyi Survey Telescope. But because the name Large Synoptic Survey Telescope and the acronym LSST, because that's been around for the best part of 10 years or so, even though the telescope has been renamed the Simonyi Telescope, they wanted to keep LSST as an acronym. So they decided the telescope's been renamed, but the project it's going to be involved with is going to be called the Legacy Survey of Space and Time. Very cleverly keeping LSST, which means the web address, lsst.org, doesn't need to be changed. Great idea. And it's called a survey of space and time because it's not just going to survey what's out there by looking at the sky and taking a picture of everything. That's been done before. What it's going to do is take a picture of the sky as often as possible, again and again and again and again. So you can see not only where things are, you can see how things change. So that's why it's an important survey that's going to be carried out once this telescope is operational in a few years' time. Remember I said that the Hubble Space Telescope has got a very small field of view, so Hubble, and indeed the James Webb, are not the sort of telescopes that you would use to survey everything that's out there because their field of view is so limited, you would not be able to cover all the sky in anything like a reasonable length of time. It would take you about a century to try and map out the sky. The imaging of the LSST, I'm just going to call it that for simplicity up till now, this new telescope, the LSST, has got a much larger field of view. There's the moon, which is half a degree. There's the tiny field of view of the Hubble Space Telescope. The field of view of this new telescope, by comparison, is absolutely huge. So large, I can't actually fit it on this slide. It's a circle that you can just imagine being completed by that blue line. It is absolutely huge, thousands upon thousands of times larger than the field of view of the Hubble or the James Webb or other comparable telescopes. How do you get such a large field of view in a telescope? Inside the Hubble Space Telescope, the main camera has a chip in it which is 40 millimeters on a side. It is that size, 40 millimeters square. If you want to make a camera and a telescope combination that sees a much larger chunk of sky, one thing you need is a big mirror. You want to collect an awful lot of light. So that's the mirror blank when it was originally made. You can obviously get the scale from looking at the number of people. I know it looks more like a Christmas cake, but it is actually a glass blank. Before, it's been ground to the right shape and then covered in metal to make it reflective. But there's no point in making a huge mirror. If you want to cover a large chunk of sky, of course, you're going to need a large camera and you're going to need a large detector to make sure you capture all the light from this large mirror. So that's not it. No, that's just for comparison. That is the size of the camera that's probably in your mobile phone, just to give you an idea. You know it's small because you ignore it when you pick up your phone. You don't even think about the fact that there must be a lens and a detector inside. You can see that the lens is just 1 millimeter or 2 in size, and the detector is just 1 millimeter or 2 in size. By comparison, the chip in the Hubble Space Telescope is 40 by 40 millimeters, and that, if you were to put it on your finger, gives you about the same scale. It gives you an idea of the scale. So how big is the chip that is picking up the light in the LSST, which has to be larger because we want a much wider field of view? Well, let's imagine just taking the 16 million pixels in the Hubble Space Telescope. You might say, well, so what? My camera's got more than 16 million pixels in it. If you've got a bridge camera or a mirrorless camera or a digital SLR camera, you might have more than 16 million pixels, and your detector in your camera might be not much smaller than that. But in the LSST, what they've taken is a chip that size, 4 by 4 centimeters, with 16 million pixels, and they've surrounded it with another 8 to make a sort of mega chip, if you like. And they didn't stop there. They said, well, if we've got this little package of 9 chips, why not take that package of 9 and add another 8 and add another 12 and then add a few more chips which are making sure that the telescope is pointing in the right direction and to make sure that it's all focused correctly. That's what they've ended up with. And getting the scale of this particular detector and comparing it with the Hubble is a bit tricky unless you happen to have a 1-to-1 scale mock-up of the chip. That is the size of the detector in the camera. You can imagine how big the camera is. The camera is easily the size of a small car. The detector is this size, and the pixels are just as small as they would be in any other camera. So there aren't millions of pixels in a detector like this. There are literally billions of pixels, and that is what can be captured in one image. It can capture 3 billion pixels worth of information. So it's the size of a coffee table. It's about 0.6 meters on a side, and it can record 3 billion pixels of information, and the information is read out in a couple of seconds or so. And the intention, because it's going to be surveying the sky, is not to spend ages on any given object. It's literally going to take a picture every 15 seconds. It's going to take a 15-second exposure, and then it's going to move on. It's going to take a couple of exposures just to make sure everything looks right, and then it will move to a different patch of sky and take another exposure. And it will be taking picture after picture after picture all night, every clear night, for 10 years. So, and each picture it takes is going to be 3 billion pixels. Now, of course, I can't possibly show you what those pictures are going to look like. I cannot put a 3 billion pixel image onto the screen. My laptop can't do it, and this TV can't do it. Just to give you a flavor of what the images are going to look like, just imagine taking that tiny, tiny, tiny black square there and say, what would we see inside that black square if we took a 15-second image of the sky? And the answer is we would see something like that. That's just a simulation. That's 1 million pixels, and in that image you can see you've picked up thousands of stars, probably thousands of galaxies, probably hundreds of objects in the solar system like asteroids and comets and trans-Neptunian objects, etc. And remember how small that is on the chip. The actual image you get in 15 seconds will be 3,000 times bigger than that. And in 15 seconds you get an image. 15 seconds later you get another image. And it will be mapping out the whole sky. It's estimated Yeah. One of the problems is having enough disk drives to hold all the information. It won't be generating gigabytes of images per night. It'll be generating many, many, many terabytes of information per night, every night that it's running. And they also have to squirt this down the internet and get it from South America to North America. And yes, they have plans to do that. How do you get the internet speeds to get from South America to North America at this sort of rate? Well, you ban all of the cat videos that would otherwise be clogging up the internet, and that gives you a much higher rate of speed. So it's going to be phenomenal in terms of the amount of information that's going to come out of this. It's going to be looking at, amongst other things, not all of the stars, a lot of the stars in the Milky Way. Now, the Milky Way has an awful lot of stars. The intention is to catalogue quite a few, possibly 10 billion stars. In other words, by the time it's looked at the whole sky, of course you can't see the whole sky in one night. You have to wait a few months for different parts of the sky to come into view. But after a few months, when it's effectively imaged the whole sky, it will have catalogued the positions and the colors and the magnitudes and the movements of something like 10 billion stars. That's a fairly large chunk of all the stars in the galaxy. And it will have also catalogued the position and the colors of many tens of billions of galaxies as well. That's the intention, to build a catalogue of close to everything that's out there. Not quite everything that's out there, but a large fraction of all the stars in the galaxy and a large fraction of all the galaxies in the observable universe. Along the way, it might help us understand what's going on with dark matter. This is just an artist's impression. We think dark matter is out there. It's producing a gravitational effect that we can see because it determines how stars behave in galaxies. It determines how galaxies behave in clusters. So we think dark matter is out there, but we don't know exactly how it's distributed. Is it uniformly distributed through a solar system, through the galaxy, between galaxies? Is it patchy? Maybe if we can survey everything that's out there, we can get a better idea of where all the dark matter actually is. And we'll do that not by seeing the dark matter, but by seeing everything else and deducing where the dark matter actually is. So as well as the survey telescope, we're also in the process of building large telescopes like the European Extremely Large Telescope. Again, for those that are struggling, there's a standard 1.8 meter high person just for scale. You can see that these things are truly enormous. There it is on the right-hand side to scale with everything else, the largest telescope that is planned at the moment. There's also a 30-meter telescope in the top right there. That's having problems because they wanted to build that in Hawaii, and there are reasons why they have not yet done so. But the Extremely Large Telescope in Chile is under construction, and hopefully it'll be ready in a few years. That may or may not be the largest optical telescope ever made, because making anything bigger is going to be quite expensive. But that didn't stop them saying, well, what if we wanted one that's 100 meters in diameter? Why can't we build one that size? And the answer is, well, you can, but it's rather expensive. So that's why they downscaled it to the size of the Extremely Large Telescope. But what would you call it? Because we've already had the Very Large Telescope. We've got the Extremely Large Telescope. So the red circle would be called probably the OWL, the Overwhelmingly Large Telescope. So no one anywhere has got any money to build this. So it's just an idea, as it were. And some people say it'll never be feasible to make one that size, but other people disagree. So the bottom line is we need lots of different types of telescopes. We need survey telescopes that are capable of scanning the sky and basically mapping out everything in the sky every 3 days or so, which is what the LSST is going to do. It's going to find all of the interesting objects that are out there. It's going to catalogue billions of stars and galaxies and lots of other objects, including, for instance, supernova. Up till now, we've seen about 1,000 supernova. If you go throughout entire recorded history, every telescope that's ever been built, add them all up, we've seen about 1,000 supernova over the last few centuries. It's thought that the LSST will probably catch 2,000 supernova in its first night of operation. and then it will continue doing that. In other words, it'll double the number of supernovae we know about within 24 hours of it being switched on, effectively. So we need survey telescopes like that to find out what's out there. Then we can tell the extremely large telescope, go look at this object in more detail. Go look at that object in more detail. And we can do the same with space telescopes, which are above the Earth's atmosphere, and hopefully we'll see yet more detail, such as the Hubble and the Webb. With all of these telescopes working together, then we'll be able to answer some of the great unanswered questions about the universe. And perhaps more importantly, we'll find out the questions we haven't even thought to ask yet. Thank you for listening.